indeterminate differences. Sometimes you can rearrange these and make them L'Hopital ready. So if we have infinity minus infinity, that's something we can't deal with on its own. It's an indeterminate form, but not a L'Hopital ready indeterminate form. So if you have a couple of fractions, like we do in this example, a couple of rational expressions, we have 1 over the natural log of x, and we have 1 over x minus 1. Well, if we try to just plug 1 in for x here, we get 1 over 0 minus 1 over 0. So, bad stuff. So let's get a common denominator. Luckily, they both just have 1s in the numerator. Makes it super easy to get the common denominator. We multiply this term by x minus 1. We multiply this term by the natural log of x. And then down below, we have the natural log of x times x minus 1. Now what happens when I plug 1 in? I get 1 minus 1 minus the natural log of 1, which is a big fat 0, divided by natural log of x, which is 0, times 1 minus 1, which is big fat 0. So we're L'Hopital ready. Don't have to use the quotient rule. We take the derivative of the numerator and derivative of the denominator, but we do have to use the product rule if necessary. Derivative of x is 1 minus 1 over x. First times the derivative of the second plus the second times the derivative of the first. Okay. Not liking this. I've got fractions on top of fractions. I don't like having fractions on top of fractions. So I'm going to multiply numerator and denominator by x over x. This x times 1 becomes x. X times 1 over x is 1. X times natural log of x. X times 1 over x goes away, so I'm left with just the x minus 1. Now let's see what happens when I plug 1 in. I get 0 on top. Down below, I get 1 times the natural log of 1, which is 0, plus 1 minus 1. Indeterminate again. X approaches 1 from the right. Derivative up top gives me just 1. First times the derivative of the second plus the second times the derivative of the first plus the derivative of x is 1. Well, x times 1 over x is 1. So this is the limit as x approaches 1 from the right. 1 on top. I have 1 plus multiplying by 1 does nothing. So this is 0, 1/2. Ta-da! There's the pretty answer. The first example there is very, very similar to the one we just did. I'm going to leave it for you. The second one is quite tricky because it is not just a fraction minus a fraction that you can get the least common denominator on. Let's see. I'll leave myself half a page for that. Let's look at the limit as x approaches infinity, x minus the natural log of x. And I'm going to do this one because it's not something that you would just think of doing. We're going to rewrite this. Well, first thing you do is you try to plug it in, you get infinity minus infinity as x approaches infinity. Yuck. So, we're going to factor out an x. That leaves me with 1 minus the natural log of x over x. So let's distribute. Make sure I didn't do anything illegal. X times 1 is x. X times natural log of x over x. Cancel, cancel. Natural log of x. So I didn't do anything wrong. It's still the exact same expression. But now I have the limit as x approaches infinity of infinity times 1 minus, well, this is natural log of x over x. That's 1 minus infinity over infinity. So infinity times 1 minus infinity over infinity. But laws of limits say I can write this as the limit as x approaches infinity of x times the limit as x approaches infinity of 1 minus natural log of x over x. We've actually done this already. This is L'Hopital ready. Limit as x, well, we haven't done that, but we've done similar ones. So I can distribute this limit as x approaches infinity of 1 minus the limit as x approaches infinity. Now that's an indeterminate form that our old pal L'Hopital can deal with. Just an x there. X approaches infinity of x times 1 minus, I went ahead and took that limit as x approaches infinity, 1 over x over 1. Limit as x approaches infinity of x is equal to infinity. This thing shoots off to infinity. I'll go back and do this one, and then we have one last thing to look at, which is indeterminate power. After a bunch of work, I ended up with 0. But that's okay. Sometimes 0 is the answer. Remember, 0 over 2 is not indeterminate. It's 0. So, indeterminate powers. If we have 0 to the 0 power, we don't know what that is. If we have infinity to the 0 power, we don't know what that is. If we have 1 to the plus or minus infinity power, we don't know what that is. So, we have to rearrange it, and we're going to do something that's very similar to logarithmic differentiation. We're going to take the natural log so we can bring that exponent down. Then we'll use L'Hopital, but because we took the natural log, we're going to have to get our final answer by taking e to whatever answer we got when we took the limit of the natural log. So we take it as natural log, and then we take advantage of the fact that the natural log, e to the natural log of a number is equal to the number. Okay, so write our steps down. Let y be equal to our functions, f of x to the g of x. Then we take the natural log of y, and I'm going to go ahead and let g of x fall down. Then we take the limit of the natural log of y is equal to the limit of g of x times the natural log of f of x, which means that our original limit, the limit of y, is equal to e to the limit of the natural log of y. So we'll do this limit, then we'll take e and raise it to that power. Let's look at an example. It'll make more sense. So first thing I'm going to do is I'm going to simplify my function. And this is example 9. I'm going to say that y is equal to 1 plus sine of 4x, whole darn thing, raised to the cotangent of x power. So natural log of y is equal to the cotangent of x times the natural log of the sine of 4x. Now I'm going to take the limit as x approaches 0 from the right. Of cotangent of x times the natural log of sine of 4x. So, as x approaches 0 from the right, cotangent, which is cosine over sine, approaches infinity, and natural log of 0, actually, it's not divided by. So this is equal to negative infinity and sine of 4x. And now you're sitting out there saying, you lost that 1, Miss Schleeper. I did, I lost that 1. That's why I was getting confused, because I was getting infinity times negative infinity, which wasn't what I expected. I expected infinity times 1, which is exactly what I have here, because cotangent goes to infinity, and natural log of 1 plus sine of 4x goes to natural log of 1, which is 0. So now I have what I expected, and life is good again. Limit as x approaches 0 from the right. I'll rewrite it. I'm going to leave natural log on top. And cotangent on the bottom is the same thing. 1 over cotangent, excuse me, because I have to put 1 over cotangent is the same as just plain old tangent down below. And now when I try to plug things in, I get 0 over 0. Limit as x approaches 0 from the right, natural log of this is equal to 1 over 1 plus sine of 4x times 4 cosine 4x, all of that divided by secant squared of x. Well, sine of x is equal to 0, so this would be equal to 1 times cosine of 0 is 1. 1 times 4 over 1, which is 4. So my original limit as x approaches 0 from the right of y, 1 plus 4x to the cotangent of x is equal to e to the 4th power, because I have to undo that natural logging I did by exponentiating. Okay. Got a couple more examples. I'll write those up for you. Practice, practice, practice. You have a quiz just on the L'Hopital's rule stuff.